We've introduced the notion of equivalence relation, and we have proved that is equivalent modulo 5 is an example of an equivalence relation. It satisfies the properties. In this lecture, we shall see that equivalence relations in general may be thought to partition the set on which they are defined into classes, called equivalence classes, with some pleasant properties. Recall that a relation R on a set A is an equivalence relation if R is reflexive, symmetric, and transitive. Perhaps the prime example of an equivalence relation is equality defined on a set A. Equality is reflexive, symmetric, and transitive, as you can probably easily establish right now. So it is an equivalence relation. Another example of an equivalence relation is the relation is equivalent modulo 5. As we have extensively proved in the previous lecture, it is reflexive, transitive, and symmetric. And we shall now see that an equivalence relation may be thought to partition the set on which it is defined into classes. Taking this particular example, the relation is equivalent modulo 5 partitions the set of all integers into 5 distinct classes if we group together all integers that are related according to the relation. The groups are called equivalence classes. For instance, one of the equivalence classes includes the integers equivalent to 2 modulo 5. Indeed, note that modulo 5, 2 is equivalent to itself, to -3, and also to 7. It is convenient to introduce special notation for the set of all integers equivalent to 2 modulo 5. Note that we also have that modulo 5 -3 is equivalent to itself, to 2, and to 7, and in fact to all other integers that are equivalent to 2 modulo 5. The set of all integers equivalent to -3 modulo 5 is exactly the same set as the set of all integers equivalent to 2 modulo 5. We shall see shortly that this is not just a peculiar property of the relation is equivalent modulo 5, but a straightforward consequence of the fact that is equivalent modulo 5 is an equivalence relation. Yet another way to describe the considered group of integers is as the set of all integers equivalent to 7 modulo 5. We proceed now to define the notion of equivalence class more generally for an arbitrary equivalence relation R defined on a set A. Consider an arbitrary element denoted by small a of set big A. Its equivalence class is the set of all elements of big A that are related to small a. We denote the equivalence class of small a by placing it in between square brackets with the subscript R. And often, when R is clear from the context, we shall omit the subscript, and we shall just speak of the equivalence class of A. Now, using that R is an equivalence relation, it is possible to establish some convenient properties of its equivalence classes. We shall prove 2 such properties in this lecture. First of all, we shall prove that everything is an element of its own equivalence class. And then we shall also prove that every 2 elements of an equivalence class are related according to R. We proceed first with the first property, proving that every element is in its own equivalence class. We want to prove that every element is in the equivalence class determined by it. So we should establish that A is an element of the equivalence class of A for an arbitrary element of A. We can apply the definition of equivalence class and then use the property of element of to simplify our goal. We find that it suffices to prove that small a is an element of the set denoted by big A, and small a is related to itself. Note that it is immediate from the assumption in the flag that small a is an element of big A, so it remains to prove that small a is related to itself. Now we use that R is an equivalence relation, and hence is reflexive. Note that we get ARA by means of a for all elimination with A on the formula stating that R is reflexive. We have constructed a complete derivation for the property. It remains to turn the derivation into a proof. To establish the required universal quantification, we declare small a as an element of big A and state that our goal is to prove that small a is an element of the R equivalence class of small a. With an application of the definition of R equivalence class and the property of element of, we can further simplify our goal to prove that A is related to itself. and then this follows by reflexivity. Here you see the resulting proof that every element is in its own equivalence class. We proceed to prove the second property. Every two elements of an equivalence class are related according to R. We first state the property as a formula with quantifiers. Note that it involves two universal quantifications. To establish these universal quantifications, we first declare an arbitrary element small a of the set big A, and declare two arbitrary elements x and y of the equivalence class of small a. The goal is then to prove that x and y are related according to R. We use the definition of equivalence class and the property of element of on the formula stating that both x and y are in the R equivalence class of A. This gives us that A is related to x and A is related to y. Using that R is an equivalence relation, we now get that x is related to y as follows. First, since R is symmetric, we may conclude that x are A from A are x. Note that we use the formula for symmetry by first applying a universal quantification elimination with A and x, and then applying an implication elimination with A are x. Then, since R is transitive, we may conclude that x is related to y from the facts that x is related to A and A is related to y. Note that we use the formula for transitivity by first applying a universal quantification elimination with x, A, and y, combining x r A and A r y with an application of conjunction introduction, and then applying implication elimination. The derivation is now transformed into a proof as usual. The proof first declares the appropriate variables, a, x, and y, assuming that x and y are both elements of the R equivalence class of A. Then, the definition of R equivalence class and the property of element of are applied. All this yields XRA and ARY, so we can conclude XRY using that R is an equivalence relation. First, we apply symmetry. Then, we apply transitivity. And here is the proof that every two elements of an equivalence class are related according to the relation that determines the equivalence class. Both general properties of equivalence classes have now been established. Every element is in its own equivalence class, and every pair of elements of an equivalence class are related. This concludes our discussion of equivalence classes and also concludes our discussion of relations in general.